So we will now consider cycles. As we have seen before, cycles are very natural concept. So this is cycle, and that's very natural concept. And also, it's important because it's related to many other concepts. As we have seen before, the codices or exactly the axis that doesn't lie in any cycles. And cycles were somehow closely related to the how connected the graphs are. And also it was related with the minimum degree. We have seen that when minimum degree is delta, you can always find the cycle with length at least delta plus 1. Okay, so we will further explore the relations between cycles and connectivity and cycles and minimum degree. Cycle and connectivity. We will explore the relation between them and cycle length and minimum degree. Okay. For connectivity, we have seen that between two vertices, if you are K connected, you can find the K passes between them. And in particular, if K is 2, that means between two vertices, you can find the two independent passes, which means cycle containing two vertices. So when you specify two vertices, you find the cycle containing both of them. A natural question is that can you generalize this into higher connectivity? Instead of finding this, can you find, say, if there are 4 vertices, and then if your graph is, say, 4 connected, can you find passes in this manner so that you find the cycle containing all 4 of them? That is a natural question. And indeed, Dirac in 60 proved this. For KLS2, each set of K vertices on K connected graph. She lies on some cycle in G. That means no matter which K vertices you take, you can find the cycle containing all of them. And surprise, surprise, we again use induction. So we use induction on K. For the base case, as I mentioned, using Mengel's theorem, if we find the two independent passes, X and Y, is cycle containing X and Y, and such passes are guaranteed. By Mengel's theorem. For higher connectivity, what can we do? We know that K connected graph is also K minus 1 connected, meaning that you have a cycle. By induction hypothesis, you have a cycle containing K minus 1 vertex. And then if it contains the final vertex as well, then we are okay. Otherwise, there is one vertex outside. And what we want to do is we want to find the cycle containing both of them, all of them. Then our idea is use band. So we find a band between X and this. As soon as we find such point, then we can take this cycle, including this X, while giving up some segment. Then make sure that segment does not contain our, vertex of interest. Then you obtain a desired cycle. So that's roughly the intuition. So for K at least 2, K bigger than 2, but as a K connected graph, G is also K-1 connected. G has a cycle C for, let's say, S the arbitrary set of spread K. Through the S, reaching the one vertex. If we consider two cases, if this cycle has K-1 vertex, then it's just cycle consists of the vertices in S, except the X. Then X is fan, which is guaranteed by fan lemma, passes its C only at the ends, and we use two successive passes. We augment C to include that. And if this contains more vertices, then using K connectivity, then you can obtain, by using fan lemma, you can find the XBC fan of size K. So, like K-1 here, but here it has size K. And what? Those K vertices actually partition that are all vertices between, partition the segment of the cycle into K segment. No, K-1 segment, sorry. Partition this vertices in the cycle into K-1 segment. It's starting and ending not ending, let's say starting with I element of S minus X, meaning that let's say you have this cycle and if the blue ones are the ones in S, and we take this one vertex and this two vertex, this three vertex as a segment. It starts with the first one, and then it starts with the vertex in S minus X starts with the vertex S minus X. You can take you can either take this direction or this direction, but it doesn't really matter. Then what? You have this K minus 1 segment, but the fan has size K. So by Pigeon principle, two of the paths HC in the same segment. So you have X, and you know that the two of them is in the same segment. Then again, you can detour and then augment this cycle. The detour from C along these passes. They absorb X between two vertices of S minus X. This shows that in K connected graph, because we can find the K fan, you can actually include this, find a cycle, including all these K vertices you pre-specify. Okay, so this is one good example of relationship between cycles and connectivity. And now we come back to the cycle length and minimum degree. So what is the longest possible cycle length? If you have n vertices, then longest cycle you can get, you can hope for, it has cycle length n. And we give name for such a special cycle. Cycle of length n is actually spanning cycle because it has to include every vertex. The spanning cycle, we call this as a Hamiltonian cycle, or sometimes it's Hamilton cycle, sometimes it's Hamiltonian cycle. So both terminologies are accepted. And a graph is called Hamiltonian. If it contains Hamiltonian cycle. So, when can we find the Hamilton cycle? So, if we know that if delta is the minimum degree of G, then you can find the cycle over length at least delta plus 1. So that implies that the minimum degree n minus 1 G is Hamiltonian. However, this is too strong condition. This implies that G is a complete graph. So, n at least 3. That's too strong. In fact, much weaker condition than this already guaranteed that G is Hamiltonian. So that is Dirac's theorem. So when G is an n vertex graph, if n is at least 3 and minimum degree is at least n over 2, then it's Hamiltonian. And this condition is best possible. So when this condition cannot be improved anymore, we say that the bound is short. Meaning that if you decrease this number by any amount, so by the minimum possible amount, then this is not true anymore. Example, you can take n minus 1 over 2, say, vertices here, n plus 1 over 2, say, shielding here, floor here, and then complete bipartite. Then this does not contain Hamilton cycle. So, and this almost satisfies this, as in that its minimum degree is at least n minus 1 over 2 floor. Very small amount shy of this. I mean, minimum possible amounts shy of this bound. Okay, so we want to prove this. And actually, there are triangle theorem called Euler theorem, and we want to prove this instead. So again, G is the n vertex graph. And if n is at least 3, and every two non-adjacent vertices, U and V, their degree sum is at least n. Then G is Hamiltonian. So again, this is sharp by the same example here. Or, there are another example. You have a complete graph, n over 2 floor, n over 2 shielding. And this is not connected. So this doesn't contain a Hamilton cycle. And this is another example of showing that the bound is sharp. So this bound is also sharp. If you replace it with n minus 1, this is no longer true. So we want to prove this. And so it's almost immediate that Euler theorem implies direct theorem, right? If minimum degree is at least n over 2, then no matter which two vertex you take, their degree sum is at least n. So this condition satisfied. The Euler's theorem implies that under this condition you can find Hamilton cycle. Okay, so how we will prove this? We'll prove this using its Euler's lemma. Its Euler's lemma. Lemma. But U and P is distinct, non-adjacent vertices on n vertex graph H. And if degree of U plus degree of B is bigger than n, then what? We show that G is Hamiltonian if and only if G plus UV. If you add this H UV, if this is Hamiltonian. So actually, this direction is easy, right? If this is Hamiltonian, you add an H, then this is again Hamiltonian. So the main point is proving the other. So if G plus UV is Hamiltonian, but G is not, then what? What happens? There must be a Hamilton cycle in G plus UV, but once you delete UV, it is no longer a Hamilton cycle. Then UV writing or spanning cycle. G plus UV. So we take one of them, let P1 to Pn. So you have a spanning path from P1 to Pn. spanning path from, say, B1 is U to Bn is B. Then what can we do? What we are going to do is something called Soda's rotation extension method. If there is this set and this set, and you can take a Hamilton cycle that does not contain UV, so which is a contradiction. So if some neighbor of U immediately follows it is U, it is B, neighbor of B on the path, say UB I plus 1, and PUI, PPI are both achieved. Then omitting PI plus 1, here is the spanning type. So what? So that S be the all I, such that the UPI plus 1 is in G, and T be the all I, BPI plus, sorry, BPI is in G. Then what happens? This counts the number of neighbors of B, and this counts the number of neighbors in U. Its neighbor, if it says neighbor, then we count the I, but it's just shifted. But still, this has size same as the degree of U. Its sum is at least n, because UV satisfies it. And what? S and T are both subset of bracket n minus 1. It's between 1 and n minus 1. So this here is from B2. So U1 has neighboring B2, B3, B4 to Bn. So this is between 1 and n minus 1. This, again, Bn itself is B. So Bn is not included here. So it's between n and n minus 1. I mean, 1 and n minus 1. So there are n numbers all squashed into n minus 1 set. So there exists I in that belong to both of them that yields Hamiltonian cycle energy, which proves the theorem. Now we have this Euler's lemma. Now, in order to prove this Euler's theorem using this Euler's lemma in a convenient way, we define the following concept. We say that a Hamiltonian closure, so for a given graph, we define Hamiltonian closure of an n vertex graph G, which we denote by C of G, is some graph we obtained from G by iteratively add edges joining sorry, so iteratively add edges joining two non-adjacent vertices. whose degree sum is list n until no such pair remains. And we say this Hamiltonian clause if its Hamiltonian closure is itself. Okay, this is a concept, but we need to check that this closure is well-defined concept, meaning that you add this edge between non-related vertices. There are several ways to add. There could be more than one pair that you can add edges. And the order of adding does not matter. It always gives you the same closure. We can prove it. The closure of a graph is unique, meaning that it does not depend on the order of edge addition. And a graph is Hamiltonian if and only if its closure is Hamiltonian. Okay. The second assertion actually follows from Borah's lemma. If the first part is well defined, assuming we know the first part, the closure is well defined, then the second one is directly followed from Borah's theorem. Because, here we show that this addition is G and G plus one H, and then it's equivalent that each of them is Hamiltonian. And the next one. And the closure is Hamiltonian if and only if the original one. And all we have to do is we have to show that the closure is well defined from an n-vertex graph. G will form a closure G1 by adding edges E1 to ER in this order, and G2 by adding in another order, F1 to Fs in this order. Assume these two different ways of adding, and then you end up with the graph G1 and graph G2. We want to show that both of them are same. Especially each addition joins vertices with degree sum at least n at that time. So if but also note that every time you add, you get a graph larger and larger, graph with more edges and more edges, so that the degree of vertices never decrease. So if pair UV becomes addable, meaning that their degree sum is at least n, then it must be added before the list ends. At some point, it should be added. It means at the end, there are no more addable pair that we could add. So let Fi be the first edge, which is omitted by G1. So also G1 and G2 are different. And by symmetry, one of them contains an edge that the other didn't. Let's say, okay, yeah, I mean, it's impossible that one contains the other as a proper subgraph, right? In that case, you should. Okay, it's actually okay. So by symmetry, let's say one of them contains an edge, the other doesn't. So Fi is an edge which doesn't belong to G1. Then what? F1 to Fi minus 1 are all in G1 because of this definition. Then what happens? Then in G union with F1 to Fi minus 1, Fi become addable because in here, that's what we did, right? But in here, when we take G1, you already have added all edges in F1 to Fi minus 1 in this list. So Fi becomes addable to G1, and it must belong to G1. A contradiction. This shows that the G2 must be subgraph of G2, and same logic is also holds. So this proves the first part, and the second part comes from the Euler theorem. Then, now what? Euler theorem is immediate. What is the Euler theorem? If you have a graph satisfying this, then for all non-adjacent pairs, its division is at least n. That means you can add all non-edges until you get the closure. So your closure, Hamiltonian closure, is complete graph. And complete graph has a Hamilton cycle. So original G has a Hamilton cycle. Okay, so that proves Euler's theorem. Finally, we proved the following theorem regarding degree sequence and Hamilton cycle. The Father theorem says it's regarding, say, for n with 3, let G be a graph with vertex degree d1 to dn. This is called the degree list or degree sequence. Degree sequence is you take the degrees of every word, then you list it in a non-decreasing way. Sometimes you use it non-increasing way, sometimes you use it non-decreasing way. So whichever one more convenient for your purpose. Well, and in here, if for all I am smaller than n, it implies that the di is at least I mean bigger than I, or dn minus I is bigger than or equal to n minus I. If this holds, then it's Hamiltonian. So there are also this branch of graph theory which considers the degree sequence. This is more general concept than just minimum degree. The degree sequence, the relationship between degree sequence and having Hamilton cycle is also natural concept. And then this quadrat theorem is implied Dirac theorem. Why? What does Dirac theorem say? Dirac theorem said that the first one is at least n over 2. That means what? The first half of them, so all the number here is at least n over 2. So for all I, this first condition always holds. So this is Hamiltonian. But the quartile theorem says that even if, some numbers are below n over 2, if there are some later numbers which are bigger than necessary, then we can still guarantee a Hamilton cycle. We can prove this. So we add it to form a closure. To form closure. Then what? And the closure surely also satisfy, because we add edges, didn't delete edges. So it also satisfies quartile condition. Then what? We know that this closure and original graph, one having Hamilton cycle implies the other. So it's sufficient to show that this closure contains the Hamilton cycle, and the original one also contains by the previous theorem. So we may assume that this closure is our graph, meaning that the G is closed, Hamiltonian closed. So our claim, we claim that if G is closed and G is not complete graph, then quartile condition fail. So if we prove this, then we are done. This means that if G is closed and then quartile condition satisfied, then it must be complete graph. So if we assume that the G is not complete graph, there exists non-adjacent pair. So choose UV such that the degree sum should say non-adjacent pair UV such that degree sum is maximum. So you have U and V, and whose degree sum is maximum, and then there are no edges between. As G is closed, degree of U plus degree of V is smaller than N. Otherwise, we would have added. Assume one of them has a smaller degree. U has smaller or equal degree, then D of U is smaller than N over 2. And we will show that the quartile condition fails for this I, which is degree of U. So what do we have? We have this choice of U and V, whose degree sum is the maximum by the choice of U and V. What? Every non-neighbor of V, every vertex which is not adjacent to V, could have played the role of U but didn't, meaning that the degree, it had degree less than the degree of U. Had degree and most du. And how many are there? And there are n minus 1 minus t of u of them. Except B, there are n minus 1 vertices. And there are degree of B many neighbors, and the rest of them are all non-neighbors. I mean, this also counts U as well. And what? Since it's the n minus 1 minus t of B, t of U is and most t of U, because sum of these two is and most n minus 1. So this is I. At least I vertices have degree and most high. Then what happened? Di, so D1 to Di are all and most I. So Di is and most I. Similarly, every non-neighbor of U but has degree and most degree of B because of the choice of UB having the maximum degree sum out of all non-adjacent pair. And there are n minus 1 minus t of U of them. But what do you know? Since degree of U is the most degree of B, U itself also has degree and most degree of B. So what do you know? Degree of B is smaller than n minus degree of U, which is n minus I. So this is smaller than n minus I. So this n minus I vertex. So this is n minus I minus 1 vertices, and together with U, there are n minus I vertices. All of them has degree less than n minus I. Hence what? D sub n minus I is smaller than n minus I. Because there are n minus I vertices, all of them having degree less than n minus I. So we have this and this. So Quater's condition fails for I. What is the Quater condition? So at least one of them has to be satisfied, but we just show that it's two. So both of them fail. So this shows that the contradiction comes from the assumption that G is not completely correct. So under the Quater condition, there are always two non-adjacent vertices which put degree sum with at least n. So apply all of them, you can keep at until you get the closure, and your Hamiltonian closure is complete. So this original graph must have Hamilton cycle because complete graph has Hamilton cycle. Okay, so far we have learned about Hamilton cycles, and also we learned about the connectivity and the useful properties of K-connected graph. And next time we move on to the next topic of coloring. Okay, yeah, so then, yeah, thank you for listening. I will see you in next video.